Assalamualaikum warahmatullahi ta'ala wabarakatuh. My name is Muhammad Hakim in Bahrain. I will present about my project, which is face recognition using Swin transformer for subject application to machine intelligence, JFB 31003. In this presentation, I will explain about complete system pipeline, final results, metric interpretation, and facilities engineering deployment discussion. This slide illustrates the complete system pipeline of the proposed face recognition system. First, the celebrity faces dataset containing 5,124 images and 32 identities was collected. Next, data pre-processing techniques such as image resizing, normalization, data augmentation, and label encoding were performed. The dataset was then split into training, validation, and testing sets with a ratio of 70%, 15%, and 15%, respectively. Subsequently, the Swin transformer tiny model with ImageNet pre-trained weights was developed using transfer learning. Next, the model was trained using the Adam optimizer with a batch size of 16 and 20 epochs, while early stopping was employed to prevent overfitting. After the model training processes was completed, the performance of the proposed face recognition system was evaluated using several metrics. These metrics include accuracy, precision, recall, macro F1 score, and confusion metrics. Accuracy measures the overall correctness of the model, while precision and recall evaluate its classification capability. The macro F1 score provides a balanced assessment between precision and recall, and the confusion matrix helps visualize the classification results for each identity. Finally, deployment considerations were investigated to assess the feasibility of implementing the proposed system in facilities engineering applications. The Swin transformer-based face recognition system can be utilized for secure access control in restricted areas, such as electrical control rooms, data center server rooms, process plant areas, chemical storage facilities, and maintenance zones. By providing contactless biometric authentication, the system can enhance security and prevent unauthorized access in industrial facilities. Next, I will present the final results obtained from training the proposed face recognition system using the Swin transformer architecture. During the training process, the model was trained for a maximum of 20 epochs. As shown in the figure, the training loss gradually decreased while the training accuracy generally improved, indicating that the model was able to learn meaningful facial features from the dataset. However, after several epochs, the validation loss started to fluctuate and the validation accuracy stopped improving significantly. This behavior suggests the occurrence of overfitting, where the model began to memorize the training data rather than learning generalized representations that perform well on unseen images. As a result, an early stopping mechanism was implemented to prevent further overfitting. The training process was automatically terminated at epoch 16, when no significant improvement in validation performance was observed. This approach helped preserve the best performing model and prevented unnecessary computational costs. At the final epoch, the model achieved a training accuracy of approximately 52.45%, while the validation accuracy was around 41.41%. Although the performance was limited by factors such as the relatively small dataset size and class imbalance, the results demonstrate the feasibility of applying Swin transformer for face recognition applications. Next, I will present the final results of the proposed face recognition system using the Swin transformer architecture. Firstly, the graph on the left shows the loss curve during the training process. It can be observed that the training loss continuously decreased, indicating that the model successfully learned the facial features from the training dataset. However, the validation loss started to stabilize and fluctuate after several epochs, which suggests the occurrence of overfitting. Secondly, the graph on the right illustrates the accuracy curve. The training accuracy gradually increased throughout the training process and reached approximately 52%. In contrast, The validation accuracy began to decrease after several epochs and remained around 41%. This behavior indicates that the model was becoming more specialized to the training data, and its ability to generalize to unseen images was reduced. Based on the performance evaluation, the final model achieved an overall accuracy of 43.77%, a precision of 28.36%, a recall of 19.21%, and a macro F1 score of 21.03%. These metrics indicate that the model was able to classify facial images with moderate accuracy, although there is still room for improvement. The relatively lower performance can be attributed to several factors, including the limited data size, class imbalance among identities, and the complexity of the Swin transform architecture. Nevertheless, the results demonstrate the feasibility of applying transformer-based models for face recognition applications. Next, I will explain the interpretation of the performance metrics obtained from the proposed face recognition system. Firstly, the model achieved an overall accuracy of 43.77%. This means that the model was able to correctly classify approximately 44 out of every 100 facial images. Accuracy provides an overall indication of the model's classification performance. Secondly, the model obtained a precision of 28.36%. This indicates that among all the identities predicted by the model, approximately 28% of them were classified correctly. Precision measures the reliability of the model's predictions and reflects the proportion of correct positive predictions. Thirdly, the recall value achieved was 19.21%. This means that the model successfully recognized around 90% of the actual facial images belonging to each identity. A relatively low recall value suggests that the model failed to identify a considerable number of true samples. Lastly, the model obtained a macro F1 score of 21.03%. The macro F1 score represents the overall balance between precision and recall across all classes. The relatively low value indicates that there is still significant room for improvement in terms of classification performance and model generalization. Overall, these results demonstrate that the Swin transformer model was capable of performing face recognition. However, the relatively moderate performance can be attributed to factors such as the limited data size, class imbalance, and overfitting during training. Future improvements may include using larger datasets, applying class balancing techniques, and performing further fine-tuning to enhance recognition accuracy. Next, I will discuss the potential deployment of the proposed face recognition system in facilities engineering applications. The proposed Swin transformer-based recognition system can be implemented in several restricted areas where secure access control is essential. One potential application is in electrical control rooms, where only authorized personnel should be allowed to access sensitive equipment and control systems. Another application is in data center server rooms, where the protection of critical information technology infrastructure is extremely important. Biometric authentication can help prevent unauthorized access and enhance overall security. The system can also be deployed in process plant areas where safety and operational reliability are major concerns. By ensuring that only qualified personnel can enter specific zones, the risk of accidents and operational disruptions can be minimized. In addition, the proposed system can be utilized in chemical storage facilities where strict access control is required to prevent unauthorized handling of hazardous substances and to maintain workplace safety. Finally, the system can be applied in restricted maintenance zone, where access is limited to trained maintenance personnel. This helps ensure compliance with safety regulations and improve the security of industrial facilities. Overall, the proposed face recognition system provides a contactless and secure biometric authentication solution. Its implementation in facilities engineering environment has the potential to enhance security, improve operational safety, and prevent unauthorized access to critical areas. Besides its potential applications, The proposed face recognition system also offers several advantages for facilities engineering environments. Firstly, the system helps to improve security and access control by ensuring that only authorized personnel are allowed to enter restricted areas. This contributes to safer and more secure industrial operations. Secondly, the use of biometric authentication helps reduce card sharing and password leakage, which are common weaknesses associated with traditional access control methods. Since facial characteristics are unique to each individual, the risk of identity misuse can be minimized. Furthermore, the system is capable of preventing unauthorized access to critical areas such as electrical control rooms, data center server rooms, and chemical storage facilities. This helps protect valuable assets and maintain operational safety. In addition, the proposed approach supports contactless biometric authentication, providing a convenient and hygienic method of identity verification. Users can gain access without the need for physical cards, keys, or passwords, thereby enhancing both user convenience and system reliability. In conclusion, the implementation of the proposed Swin transformer-based face recognition system offers significant benefits in terms of security, reliability, and convenience, making it a promising solution for access control applications in facilities engineering. Lastly, I will discuss the real-time feasibility, scalability, and future improvements of the proposed face recognition system. Firstly, in terms of real-time feasibility, the proposed system is capable of performing real-time face recognition when supported by GPU acceleration. In addition, the system can be integrated with existing access control infrastructures, making it suitable for practical implementation in industrial facilities. Secondly, regarding scalability, the system can easily accommodate a larger number of users. New personnel can be added by retraining and fine-tuning the model with additional facial images. Therefore, the proposed approach is suitable for large-scale industrial facilities with expanding workforces. Finally, several future improvements can be considered to enhance the performance of the system. This includes utilizing larger datasets to improve generalization capability, implementing better class balancing techniques to address data imbalance, and applying fine-tuning strategies to optimize the Swin transformer model. Furthermore, leafless detection mechanism can be incorporated to protect the system against spoofing attacks using printed photographs or digital images. In conclusion, the proposed Swin transformer-based face recognition system demonstrates promising potential for deployment in facilities engineering applications. With further improvements, the system can provide a more curable, scalable, and secure biometric authentication solution for industrial environments. Thank you.